Welcome to the workshop. We want to continue taking a look at section 2.5, Mathematical Induction. Before you get into this video too far, I'd like to give you just one heads up that we're going to be looking at sigma notation or summation notation. So if you're unfamiliar with these ideas, we saw them actually back in section 1.4 while trying to count the number of elementary operations in an algorithm. But if you're unfamiliar with them, you may want to just give a quick review before you watch this video. Hopefully you had seen it in calculus, so you should be aware of it. If you're not, or if you're not quite sure what I'm talking about, take a look at this in just a moment, and then go ahead and review what you need to make sure you know what's going on as we consider this proof. All right. Let's look at our problem. So we want to prove this statement by mathematical induction. Proving something by mathematical induction first requires that we observe what the statement is. Then we have to show that the base case is satisfied. Then we have to show that the inductive step is satisfied, and then we can make our conclusion. Now, when it comes to a proof, any proof, it should begin by indicating that you're starting a proof, and there should be something that indicates that you're done with the proof. To show that you're starting it, we simply write proof. To show that it's over, we draw a box and fill it in on the bottom right. Okay, so these are the incredibly basic outline of a proof by induction. The statement that we would like to prove is that the sum of the integers from 1 to n is n times n plus 1 over 2. Again, you should be familiar with this. There are a lot of examples that use this summation. So we'd like to prove it here. All right. So we have a proof by induction, and the statement in this case is that the sum of the integers from 1 to n, okay, the sum of I from 1 to n is equal to n times n plus 1 divided by 2. And this is for any integer greater than or equal to 1, right? Because it's for all positive integers. So our base case is going to be when n is equal to 1. All right, so our base case. The base case here, we want to let n be equal to 1. Then I consider the left-hand side of the equation, right? The left-hand side of the thing I want to show. Whenever there's an equality I want to show, I evaluate the left-hand side, I evaluate the right-hand side, and then I observe that left-hand side and right-hand side are equal to one another. That's how you should check for equality. So the left-hand side is equal to the sum from I equals 1 to 1, because we're letting n be equal to 1. This is just, in fact, 1. And the right-hand side in this case is equal to, we're letting n be equal to 1, so this is 1 times 1 plus 1 divided by 2. And it's a good idea to show the plugging in of the value for n, right? I plugged in 1 for n. Here's what I got. I plugged in 1 for n. Here's what I get. If you want to show some algebra, great idea, right? 1 times 1 plus 1 is 1 times 2, still divided by 2, of course. The 2's cancel out, so it's just 1. Thus, S of 1 is true. Yay! Okay, so the base case is true, and we see that because the left-hand side and the right-hand side are equal to one another. Left-hand side equals right-hand side. Perfect. All right, the next thing that we want to show is the inductive step. So we want to show that the inductive step is satisfied. So the base case gives us a starting point. The inductive step allows us to move from the starting point forward. So the inductive step needs to work for anywhere that we're at in the integers. So we can't say let n be equal to 1. Let's show it right? Sorry, we can't say, let's assume it's true for 1, let's show it's true for 2, because then we'd still have to show it's true for 3. And we have to show it's true for 4 and move on. And that's just going to be time consuming. It never end because the integers never end. So what you have to do is you have to say, no matter where we're at, if it's true here, and we can then know that it's true at the next spot, then we'll always be able to move forward, whether we're starting at 1 or whether we're starting at 52. Okay, so here we want to assume that S of k is true for some integer greater than or equal to the base case. Okay. What I want to do then is show that S of k plus 1 is true. Excellent. Well, if I want to show that S of k plus 1 is true, I really need to know what I'm trying to show here. So as a side note, right, to know what I'm trying to show, I'm plugging in k plus 1 into our summation, summing from 1 to k plus 1. And according to our statement that we're trying to prove true, this should be equal to, well, I'm plugging k plus 1 in for n. So I have k plus 1 right here, and then times k plus 1 right here, plus 1 divided by 2. So I have my n, and I have my n. N times n plus 1 over 2, where my n in this case is k plus 1. So I'm going to start with the left-hand side and then find the right-hand side. But before I do that, it's sometimes a good idea to say what this means for us. So what does it mean that S of k is true? Well, that tells us, I need to change the color back here. That tells us then the sum from I equals 1 to k of I is equal to k times k plus 1 divided by 2. Right? That's the statement. This statement is true for k. Now we want to show that it's true for the next thing. So we look at the sum from I equals 1 to k plus 1. And I want to show that this is equal to what I wrote up here. I want to show that it's equal to this. But I need to do some work because I don't simply have that it's true. I need to show that it's true. So what I do here is I perform some manipulations. The first thing that I do is I say that this is equal to the sum from 1 to k. But hey, don't I have one more term in there? Yes, I do, right? I have the k plus 1 term, and the k plus 1 term is just k plus 1, right? Because I'm plugging in k plus 1 here. So I have that one additional term, but I know what this is equal to, right? This thing is equal to k times k plus 1 divided by 2, because I assumed that it's true for k. And then what I can do here is I can say, well, that's plus 2 times k plus 1 divided by 2. So now I have a common denominator. With a common denominator, I can combine fractions. So I might not know where exactly this is headed. Now, of course, I do, but when I first write this up, I might not know where it's headed. I just know that this thing is only one fraction. So I split it up so that way I can use what I know about S of k, the fact that it's true. That gives me one fraction, and then I go ahead and create my other term with a common denominator so that I can add them and have one fraction. Excellent. So this gives me k times k plus 1 plus 2 times k plus 1 all over 2. So this looks good. Now, just as a quick note here, I can observe that I have a k plus 1 and a k plus 1. So my 1, 2 terms in the numerator have a common factor of k plus 1. So since I have a common factor, hey, let's go ahead and factor that. So I've got a k plus 1 over here, and what I'm left with is k plus 2. And that looks pretty good, all over 2. Now all I have to do is notice that I have k plus 1 times k plus 2 is k plus 1 plus 1, right? Yeah, of course it is. And that gives me exactly what I wanted to show. K plus 1 times k plus 1 plus 1 divided by 2. K plus 1 times k plus 1 plus 1 divided by 2. Thus, S of k plus 1 is true. So I've showed that whenever it's true for k, it's true for k plus 1, which means I can continue to move forward. So I know it's true for 1, and knowing it's true for the next case always, and then that tells me it's true for 2, and it's true for 3, and 4, and so on. And we can continue on. So we've shown it's true for the base case, we've shown it's true for the inductive step, and the principle of mathematical induction says that it's true for all integers greater than the base case. So thus, by the principle of mathematical induction, S of n is true for all integers, for all positive integers, is what we're interested in here. And I indicate the end of my proof with a square that's been filled in. So that's our proof. And they should all look like this. They should all look the same in terms of the structure. They begin with proof. You show the base case, right? I suppose you begin with proof, you identify your statement and which value the base case is. Then you show the base case is true. Then you show the inductive step. And then, right, all of this is the inductive step. And then you have your conclusion. Every proof should include that. In particular, the proofs by induction should have this exact same structure. Indicate the beginning of your proof with the word proof. Notice I tabbed over for everything, right? So it's all tabbed over. You should do that too. That's just good housekeeping. It's good organization. So indicate proof. Identify the statement and the base case. Prove the base case. Or show the base case is true, rather. Show the inductive step is true. Show that the base case and the inductive step hold. However you want to phrase it, you're just showing that S of 1 is true or S of 3 is true, whatever the base case is. And then for the inductive step, you assume it's true for K. What does that tell you? It tells you this. All right, let's show that it's true for the next one. Okay, hey, look, equality. Took my thing on the left-hand side and manipulated it until I had the right-hand side that I needed. Perfect. Once I had that, I can say, hey, the K plus 1 case is true. Thus, by the principle of mathematical induction, it's true everywhere. And if we don't remember what the principle of mathematical induction says, it says it right here. If it's true for the base case and it's true in the inductive step, then it's true for all integers greater than the base case. That's why at the end of our proof, we say by the principle of mathematical induction. The statement is true for all integers greater than the base case. This statement right here should look the same every time. The only thing that should change is what integers it's true for. Okay? But you should literally have, by the principle of mathematical induction, Sn is true for all whatever integers you're trying to make a statement about. That should be the same every time. All right, that's a little bit rigid, but that's so that way we have something that we're very easily able to identify if we have the right thing or not. Okay, is there more flexibility allowed in a book, in somewhere else? Yeah, maybe. But for us, for now, let's make it this rigid form so that way we know exactly what we're looking for. If we don't know what we're looking for, we're going to have a hard time finding it. So this is what we're looking for. If you have any questions or concerns, of course, don't hesitate to get a hold of me. I'll see you guys back in the workshop for more examples on mathematical induction.